abstract and introduction. So we must know that the current available models assume that the nodal demands are independent of her nodal heads and full supply. And we know that in practice that that thing didn't happen. So in that we know that we can have in nodes like a little bit discharge or disload, and that disload is a little bit proportional to his head. So if we have considered that head that is just a little bit discharged, that relationship between each node is the heat drive analysis method. Uh, so that's like the concept that we have to make the abstract situation about the article that it's trying to try to tell us. So in the part of introduction, they keep talking about the WDN, that is the water distribution network. And that leads to a more, it's just like a method that leads to a more accurate analysis, and it's just like more precisely. Uh, we know that this current model of WDN assumes that the nodal demand are still full supplied, but they are independent between each node. So that's just make a whole new world between the previous analysis and the new one. Uh, we know that this assumption is like a demand driven analysis that is take like a DDA, and we know that continuing with that assumption that creates like a little bit extra conditions to the rest. Uh, the problem is that these conditions can be take like like a little bit unrealistic when we go to practice, but we know that they really work in real life. So we know that we have like a little bit problem of pressure deficit, uh, and that it's because of pipe breaks, valve failures. I was talking about pipe breaks. So beyond pipe breaks, we got like valve failures, like pump breakdown, and like excessive consumption. That is the part of us as the people, like we use a lot the system. So as a result, we actual supply lack of flow that his consumers decreases a lot. So we are probably going to get some nuts that will not be able to supply any discharge, and it is going to be a problem to all the system and to the people that is going to be using that system. So in order to simulate the actual performance that we are putting into situation, it's necessary to consider the relationship that we are talking about his between the nodal head and the discharge that is proposed in the system.
Now we have materials and methods. In the left side of the screen, we have the head-discharge relationship in a general overview. Principally, we have the equation proposed by Wagner for relationship between head and discharge. This equation is from 1988. This equation have a restriction. These restrictions are solved for who in 2009, who proposed a threshold pressure, and for this range of pressures proposed this graph. In this graph, we can see that after pressure threshold, we have a demand threshold constant. That is the correction. Taking in account this, in this paper, we have a proposed head discharge relationship. This proposed taking account for conditions that we can say here. First condition, second condition, third condition, and fourth condition. And for these conditions, we have the restrictions. For the restrictions, we have that the first condition is when we have lower values than the minimum value, which provides no discharge. Discharge required and between discharge maximum, minimum, and required, and minimum of the minimum. This paper in additionally have the head leakage relationship. At the same way of the head discharge relationship, we have some equation proposed. Between the most relevant is the proposed for Yiannopoulos in 1985. And these equations take in account the discharge from the point on the pipe Fg, that is this term. C is a constant, and Lg is the pipe length, and Hi and Hj are hydraulic heads. Finally, GL is the ground levels. Total leakage discharge for each node of the network is determined and follows for this equation, that is equation 9, where this term is the leakage at node Ig and is the total number of node connect for this term.
Now with the gradient algorithm. The gradient method was proposed by Totini and Plotini. This method is based on application of the Newton-Raphson method for obtaining the unknown pipe flows and nodal heats simultaneous. In this approach, pipe flow values are summoned at first, for instance 1 liter per second. Then, by solving the linearizing equation of heat loss in pipes and linear continuity equation of nodal flows simultaneous, the improved values of pipe flows and nodal heats are obtained directly, while in another method's correction for heats and flows should be first calculated. Improved pipe flow values obtained from the first iteration are considered as the initial values for the next iteration, and this procedure continues until the maximum difference between the calculated values for the pipe flows in two successive iterations can be disaggregated. In this method, there is no need to balance the continuity equation of nodal flows to start of the iterative calculation. We have one equation for gradient algorithm, in which Q0 is the recurring nodal demand vector. Qm and Qm plus 1 are pipe flow vectors for Mt and Mt plus 1 iterations. H0 is the heat vector of fixed head nodes and simultaneous. Okay, now with head-driven analysis, in order to analyze a network with the HDA method, the constant nodal discharge term Q0 in all equations should be replaced with the heat discharge relationship. In order to simulate liquid, a new attribute which characterizes leaking for each pipe is considered a new demand category. Is definite for each node to indicate the leaking discharge. In this method, consider now with dynamic analysis of WDNS. In this method, considering the no elevation volume curve of each tank, the tank elevation at the end of each time period is. We have a equation here, in which HTK is the water elevation of the tank, Tk is the outflow volume of the tank, Tk in the period is T mass T plus delta T. Okay, in descriptions, now on descriptions and result model evaluation. In order to compare the result, the sample network was analyzed using. We use here three programs: EPONET, CWSNet, modified model. In these tables, we can observe the difference between the three programs, searching the age on the the code. Okay, result of leak simulation. The DDA method shows no variation in nodal discharge, but the nodal hits are less than the case with a leaky. Since the calculated negative hits are wrong, then the leak values obtained from the heat leakage relationship in these nodes are meaning. In this method, in this simulation, we only use two programs, that is DDA Eponet and Modify HDA bus model to search the N and the Q.
Results of leakage simulation. This network is analyzed considering leakage in DDA and HDA methods, and the results are presented in Table 5. The DDA method shows no variation in nodal discharge, but the nodal heads are less than the case without leakage. Since the calculated negative heads are wrong, then the leakage values obtained from the heat leakage relationship in these nodes are meaningless. The HDA method shows a decrease in the nodal head values. The available discharge in the critical node is less than the case without leakage as a result of the additional discharge due to the leakage. It should also be noted that the difference in the reservoirs outflows in the case without leakage is less than the total leakage, because in the network with leakage, the available nodal discharge is decreased and some amount of water that should serve the consumers is lost as leakage. It can be concluded that the associated outflow of reservoir is not necessarily equal to the total leakage of WDM. In the process of leakage calculation, the leakage coefficient and the head exponent in Germanopoulos formula are considered equal to 1.18, respectively. Results of dynamic analysis. The sample network was also analyzed using a stand period simulation within a 24-hour period and with time steps of 1 hour. The demand pattern is presented in Table 6 by substituting the reservoir in node 1 with a tank having the capacity of 1000 meter of 3. For every 0.48 and cross section of 2500 meters of 2. HDA is conducted and the variation of tanks head within a period of 24 hours is present in figure 3. A table from this figure, the tanks head changed from 100 to 19.2 meters. The values of nodal discharge and the time total outflow are shown in Table 5. As it can be seen in this table, the consumption in the critical nodes of 6, 8, and 9 in time steps with the maximum consumption are less than the required discharge. The reason is that the hydraulic heads in these nodes are less than the minimum required head. Therefore, the nodal available discharge are decreased. Figure 4 illustrates that at 7 am, consumption increased and the head in node 9 becomes less than the minimum required value. Therefore, only a percentage of the demand in this node is supplied. Also, in nodes 8 and 6, in the time steps with high consumptions, the head values are less than the minimum required value due to the decrease in the head of the tank. Therefore, the demands are not fully supplied in these time steps. Impact of the new proposed head discharge formula on HDA. In tables 8 and 9, the results of using the new proposed head discharge formula in comparison with the DDA and the ordinary HDA with one Warner formula are present in the two cases of with and without leakage. Table A shows an increase in the total flow of the reservoir while using the new formula. It is a result of head values between H required and H mass in the new formula.